Welcome to Module 4 of Cells, Tissues and Regulation. In Topic 4.3, we will learn about the action potential. During the course of this video, you can open your workbooks to Module 4 and try and answer as many questions as you can from Topic 4.3. The learning objectives for this topic are to draw and label the typical action potential curve of millivolts versus time, indicating the resting membrane potential, subthreshold potentials, depolarization, repolarization, and hyperpolarization. To explain the role of sodium and potassium channels in each of these steps. To explain the all or nothing principle of action potential propagation. To differentiate between slow and fast nerve transmission and the role of myelin sheath in this context. And finally, to understand the basic pathology that underlies multiple sclerosis and how the local anesthetic lignocaine works. Neurons transmit electrical signals, known as action potentials, along their axons, some of which are transmitted over long distances. An action potential is a brief reversal of membrane potential with a total change in amplitude or voltage of about 100 millivolts, from negative 70 millivolts to positive 30 millivolts. Only cells with excitable membranes, such as neurons and muscle cells, can generate action potentials. Other cells do not transmit electrical signals this way. This is a short review of the resting membrane potential. A voltmeter is used to measure the potential difference in charge between the 2 points. When one electrode of the voltmeter is inserted into a neuron, and the other into the extracellular fluid, it records a voltage across the membrane of approximately negative 70 millivolts. The minus sign indicates that the cytoplasmic side of the membrane is negatively charged, relative to the outside. This potential difference in a resting neuron is called the resting membrane potential. The plasma membrane separates charges locally, and therefore it is said to be polarized, meaning charged. The value of the resting membrane potential varies from negative 40 millivolts to negative 90 millivolts. The resting membrane potential exists in all living cells. Depolarization is a decrease in membrane potential, which means that the inside of the membrane becomes less negative, or moves closer to zero, compared to the resting membrane potential. For instance, a change in resting potential from negative 70 millivolts to negative 65 millivolts would be considered a depolarization. Hyperpolarization is an increase in the membrane potential, which means the inside of the cell becomes more negative or moves further away from zero, compared to the resting membrane potential. For example, a change in the resting membrane potential from negative 70 to negative 75 millivolts would be considered hyperpolarization. Repolarization is when the resting membrane potential returns to its negative value just after the depolarization phase. Finally, overshoot means the inside of the membrane is more positive due to the reversal of the membrane potential polarity. Neurons use changes in their membrane potential as signals to receive, integrate, and send information. They generate these signals in the form of action potentials that are propagated along axons. A change in the membrane potential is produced by changing the permeability of sodium and potassium ions across the plasma membrane, thereby altering ion concentrations on both sides of the membrane. The changes in membrane potential can produce two types of signals. Graded potentials are incoming signals operating over shorter distances, whereas action potentials are long-distance signals propagated along axons. Sodium permeability is crucial in changing the membrane potential of a neuron. Remember, sodium constantly tends to diffuse into the cell because of its electrochemical gradient. However, not much sodium gets into the cell because the membrane permeability to sodium is very low. The plasma membrane contains a variety of membrane proteins, some of which act as ion channels. These channels are selective as to the type of ions they allow to pass through. If sodium ion channels in the membrane were opened, sodium would diffuse through into the cell along its concentration gradient. The rapid influx of sodium would make the cell more positive. and if enough sodium enters the cell, the inside of the cell could be made positive compared to the outside, which is the depolarizing of the resting membrane potential that we mentioned earlier. In the nervous system, different channels are responsible for transmitting electrical signals over long and short distances. Some of these ion channels are gated, meaning part of the protein forms a molecular gate that changes shape to open and close the channel in response to specific signals. The graded potentials mentioned a moment ago travel shorter distances and are activated by the opening of mechanically or chemically gated ion channels, whereas action potentials are generated by the opening of voltage-gated ion channels. There are three types of gated ion channels. Mechanically gated channels open in response to physical deformation of the receptor, such as in sensory receptors for touch and pressure. The chemically gated channels, also called ligand-gated channels, open when certain molecules, neurotransmitters for example, bind to the channels. Finally, voltage-gated channels open and close in response to changes in the membrane potential. When gated ion channels open, sodium ions diffuse quickly across the membrane. These ions, flowing along their electrochemical gradient, are responsible for all the electrical events in a neuron. The flowing ions create electrical currents and voltage changes across the membrane, thereby generating action potentials. Graded potentials are short-lived, localized changes in the membrane potential. They are triggered by a change or a stimulus in the neuron's environment. These weak stimuli open gated ion channels that allow some sodium ions to enter the cell, but not in large enough quantities to generate an adequate charge to open the adjacent sodium channels. Instead, the stimulus depolarizes a small area of the neuron's plasma membrane. However, it's not enough to propagate an action potential. These localized depolarizations are what we call graded potentials. Graded potentials lose their strength as they move through the cell because the plasma membrane is permeable, like a leaky garden hose, and most of the charge is quickly lost through leakage channels. Consequently, the current dies within a very short distance of its origin and is said to be decremental. The strength of a graded potential is directly proportional to the strength of the triggering event. Graded potentials are essential in initiating action potentials, the longer distance signals. Once graded potentials reach a threshold, they trigger the propagation of an action potential by opening voltage-gated sodium channels. A neuron generates a nerve impulse only when adequately stimulated. The stimulus changes the permeability of the neuron's membrane to sodium by opening specific voltage-gated channels on the axon. If sufficient sodium diffuses into the cell, an action potential is generated. Action potentials serve as electrical signals that are propagated over long distances along a nerve cell. They can only occur if the inward movement of sodium is enough to generate sufficient electrical charge to then open the adjacent sodium channels sensitive to this charge. Increased sodium permeability due to the increased channel openings leads to greater and greater depolarization, which increases the sodium permeability, and so on. This explosive positive feedback cycle is responsible for generating an action potential. Once generated, it moves along the axon towards the axon terminals. Potentials are propagated along the axon. A single action potential is a brief reversal of the membrane potential, with a total change in the voltage of around 100 millivolts from approximately -70 to +30 millivolts. At a resting state, all the sodium and potassium gated ion channels are closed, thereby maintaining a resting membrane potential of -70 millivolts. However, when graded potentials reach the threshold, they generate an action potential. A single action potential can be divided into three different phases: the depolarization phase, the repolarization phase, and the hyperpolarization phase. Depolarization, as mentioned before, means the loss of membrane potential or polarity. As local currents depolarize the axon membrane, the voltage-gated sodium channels open and sodium rushes into the cell. This influx of positive charge depolarizes the local patch of membrane further, opening more sodium channels, so the cell interior becomes progressively less negative. When depolarization reaches a critical level called the threshold, which is usually between 55 to negative 50 millivolts, the depolarization becomes self-generating. As more sodium enters, the membrane potential depolarizes further. As sodium rushes down its electrochemical gradient, the membrane potential becomes less and less negative and then overshoots to positive 30 millivolts. This explosive feedback cycle is responsible for the depolarization phase of an action potential. The voltage-gated sodium channels that play a crucial role in the depolarization phase have two gates, the activation gate and the inactivation gate, that alternate between three different states pictured here. At resting membrane potential, the activation gates are closed, preventing the entry of sodium into the neuron. In the depolarization phase, when the depolarization hits the threshold, the voltage-sensitive activation gates open, allowing sodium to enter the cell. During this phase, the cell is 1,000 times more permeable to sodium ions. As more and more sodium rushes into the neuron, the membrane potential becomes positive, from negative 70 millivolts to positive 30 millivolts. This causes a rapid upward spike of the action potential. During the repolarization phase, the inactivation gate closes the channel and prevents the entry of sodium into the cell. After these channels are blocked, the cell cannot generate another action potential for a short period of time. This means that the only channels available are in front of the action potential, since they are yet to be opened. As a result, the action potential is transmitted only in one direction. The depolarization phase of the action potential persists for only about 1 millisecond. In the repolarization phase, the inactivation gates of the sodium channels begin to close, at this point, thus preventing the entry of sodium into the neuron. As a result, the membrane permeability of sodium declines to resting levels, and the net influx of sodium stops completely. At the same time, the slow voltage-gated potassium channels open, and the potassium rushes out of the cell, following its electrochemical gradient. This restores the internal negativity of the resting neuron, and is known as repolarization. The period of increased potassium permeability lasts longer than needed to restore the resting state. As a result, an excess of potassium escapes out of the cell before the channels can close, causing the membrane potential to become more negative than normal for a short period of time. This is called the hyperpolarization phase of an action potential. This is corrected by the slight influx of sodium over time, and the resting membrane potential is soon re-established at negative 70 millivolts. Also at this point, the voltage-gated sodium channels begin to reset to their original conformation, ready to conduct the next action potential. This is done by a change in shape to reopen the inactivation gates and close the activation gates. When a region of a neuronal membrane is generating an action potential and its voltage-gated sodium channels are open, the neuron cannot respond to another stimulus, no matter how strong the stimulus is. This period, from the opening of the sodium channels until the sodium channels begin to reset to their original resting state, is called the absolute refractory period. The absolute refractory period lasts roughly about 1 millisecond. It ensures that each action potential is a separate event and enforces one-way transmission of the action potential from the trigger point. The relative refractory period follows the absolute refractory period. During the relative refractory period, most of the sodium channels have returned to their original state. However, some potassium channels are still open, and repolarization is occurring. An exceptionally strong stimulus can reopen the sodium channels that have already returned to the resting state, and generate an action potential. Strong stimuli trigger more frequent action potentials by intruding into the relative refractory period. Not all local depolarization events produce an action potential. The depolarization must reach the threshold values if an axon is going to fire. An action potential is an all or nothing phenomenon, meaning it either happens completely or it doesn't happen at all. This phenomenon is dependent on the strength of the stimulus and the amount of sodium entering the cell. An action potential can only be generated when enough sodium enters the cell and the depolarization reaches the threshold. However, if the depolarization does not reach the threshold, which means if the number of sodium ions entering the cell are too low, then the action potential will not be generated. Furthermore, regardless of how strong a stimulus is, the amplitude or strength of a single action potential does not change, but the frequency does. Therefore, a strong stimulus will have a greater frequency of action potentials than a weakened stimulus. The connection velocities of the neuron may vary widely. Nerve fibers that transmit impulses most rapidly are found in the neural pathways where speed is essential, such as those that mediate postural reflexes. Axons that conduct impulses more slowly typically serve internal organs, such as the visceral organs, the glands, and blood vessels. The rate of impulse propagation depends on many factors, including the axon diameter, where axons with a large diameter can conduct impulses more rapidly because they offer less resistance to the flow of local currents, and the degree of myelination, because the speed of the action potential propagation can dramatically increase with more myelination. By acting as an insulator, myelin sheaths prevent almost all charge from leaking from the axon and allows the membrane voltage to change more rapidly. Here, the signals are forced to jump between the nodes separated by the sleeves of insulation, and this allows for very rapid signal transduction. Multiple sclerosis is a demyelinating autoimmune disease, in which the immune system attacks the myelin proteins. Multiple sclerosis gradually destroys myelin sheaths in the CNS, reducing them to non-functional, hardened lesions called sclerotic plaques. As a result, the signal is transmitted much more slowly, and eventually, impulse conduction stops. Patients with MS suffer from problems such as controlling muscles, difficulty in walking, speech disturbance, and vision loss. MS is most predominant in young adults. Local anaesthetics include cocaine derivatives, such as lignocaine, that block the opening of voltage-gated sodium channels. With reduced sodium entry, there is reduced action potential propagation, which reduces or prevents the transmission of pain signals, as well as causing some skeletal muscle paralysis. From this video, we have learnt about membrane potential terminology, changes in potential and sodium permeability, graded potentials, action potentials, the all or nothing rule, the role of myelin sheaths, and finally multiple sclerosis and local anaesthetics.